Hi, everyone. I'm Barry Barish. I'm the public speaker for tonight at the ICHEP 2020 meeting. ICHEP is the traditional big meeting for particle physics. It's held every 2 years. It moves around the world, and it's where particle physicists and others that are interested hear about the latest results on large accelerators, the latest theories, the latest ideas, and the new areas that particle physics has an impact. For example, particle physics now is very important in us understanding what the dark matter is in the universe, what the dark energy is in the universe, how the universe began. It's important to us in understanding quantum physics and so forth. So high energy physics has a very broad impact. So far, because it's so infantile, gravitational waves have been not part of the venue, but should be and will be. Gravitational waves, which I'll talk about today, represent understanding, again, one of the fundamental areas of physics, which is the forces. The four forces of nature are the strong interaction that holds the nucleus and us together, the weak interaction, which causes radioactive decay, the electromagnetic interaction, which is electricity and magnetism and so forth, and gravity, which we're all familiar with. But gravity is really very, very weak, and we know the least about it. What we've discovered just a few years ago is something that Einstein actually predicted more than 100 years ago, and that is that gravity has waves, just like electromagnetism has waves. And those waves were an important discovery, of course, but they give us a new tool to understand our universe. And that's the theme. I'll tell you a little bit about gravitational waves, but that's the theme that I want to explore with you tonight. So let me explore it first by getting to a full screen and showing you some slides that will that I'll talk from as we go through the lectures. So here we are. Now we're going to try to explore how we can understand more about our universe with gravitational waves. This subject that I'll come to after a little while, we can reflect a little bit first at something that we've all witnessed, but maybe haven't realized so much. That is, what has caused the dramatic advances in astronomy over the recent 50 years, say, during the 20th century and the early 21st century. It's really the fact that astronomy, as invented by Galileo, covered the visible band of wavelengths. We looked through a little lens and we saw four moons of Jupiter. And from that, astronomy was born. In 400 years, we've developed a lot of tools so that we study astronomy now in other wavelengths. We study it in the ultraviolet, the infrared, with gamma rays, with radio waves, and so forth. And most recently, we've made tremendous advances by looking at the same phenomena. Here I just show a picture of a very well-known phenomena, the Crab Nebula, looked at in different ways, looked at in the ultraviolet, looked at it in the radio waves, looked at it in visible X-rays and so forth. And it's the combination of all that that gives us so much insight now into these phenomena in astronomy. And in 20th century, in 21st century in astronomy, we've seen this even go another step, not just multiple wavelengths like I showed, but combining instruments. And all of you probably noticed or saw last year in the newspapers a beautiful picture, a photograph-like picture of a black hole. That was done by looking at instruments in the radio that are in the South Pole in Europe, in the US, in South America, and in Asia, and by all kinds of difficult and wonderful combinations of the data, made it behave like it's one instrument the size of the Earth. And with that, they had the power to image a picture of a black hole. And that was called the Event Horizon Telescope, this thing altogether. And so that is now beyond using different wavelengths, is using different instruments. Event Horizon Telescope was very complicated because of all the instruments, and really did the problem by combining this data in using modern computers on data that wasn't necessarily formatted the same or meant to be put together, but was put together to show this beautiful image of a black hole. The next frontier for astronomy is believed by many people to be part of the subjects that I'll talk about today, called multi-messenger astronomy. So by multi-messenger, what we mean is not just electromagnetic radiation. Well, it's all electromagnetic radiation if we talk about radio, infrared, ultraviolet, visible. So we just looked at different wavelengths of electromagnetic radiation, but we also could look at other messengers. Those other messengers are ones that have been found in particle physics, neutrinos, and the one that we found, gravitational waves. These come about in very, very different ways. The neutrinos by some sort of nuclear interactions, gravitational waves by the gravitational force and some changes that enable producing gravitational waves. And so from the same phenomena, we can get very, very different messages. And we've got a little start on that, which I'll show you, which is pretty dramatic, even since we discovered gravitational waves. So the idea is you use all the electromagnetic instruments, of which that's the most mature, gravitational waves, which I'll talk about mostly today, and even neutrinos. This is a picture of the neutrino detector detecting neutrinos under the ice, deep under the ice at the South Pole. So let's first try to understand a little bit about what gravitational waves are, and then work our way into the science. We all learned gravity from Newton. We learned this famous formula, which he wrote down in the Principia, which is that the force between two massive objects is the product of the two masses divided by the square of the distance apart times a constant that took another 100 years to figure out. And that's the force, and that's universal gravity. It describes why the moon goes around the Earth, why the apple falls out of the tree, the tides, and essentially everything to do with gravity as we see it in everyday life from the time 1687 until Einstein came along, with one little exception, which I'll point out. Einstein came along in the year 2000, in the year 1915, and proposed at that point a new theory of gravity. I won't explain the detailed question, but this is the equation, but this is his equivalent of Einstein's equation. And it's his universal gravity, and it's needed for reasons that I'll point out. Universal gravity, in the case of Newton, described the forces between two massive objects and what the formula is. And in Einstein's formulation of gravity, it's not a force at all. It's the fact that space and time are unified and are affected by the presence of masses and the changes of any mass distributions. And that four-dimensional space and time together is what makes the theory rather complicated to understand and to calculate. But out of that, Einstein predicted much about gravity. The only problem that existed at this time where Newton's theory didn't give the right answer, as observations had gone, is the orbit of Mercury around the sun. The orbit of Mercury around the sun is a very elliptical orbit. Each time it goes around, it's affected by the positions of all the planets and moons. And it's moved to an orbit that's a little bit like a daisy petals. And the distance from here to here, or the amount that it bends, can be calculated using Newton's theory. And it doesn't quite give the right answer. It gives an answer that's about 10% less than the actual bending that was observed. So this was the only puzzle that existed at the time Einstein came along. And in fact, it could have well been experimental. It could have been because we don't yet understand where all, at that point, where all the planets, moons, and objects are, the massive objects in our solar system. And it could also be that there's an object that might be missing that's between Mercury and the sun. In fact, that was a popular theory in the 1800s. There were false discoveries of such a planet in between, but it was never found. And as far as we know today, it doesn't exist. Einstein's theory solves this problem. It gets the right answer. That's the first requirement of a new theory. If it's going to replace or add to a theory that we already have, it first has to maybe solve some problems that the other one couldn't. So Einstein's theory solves the problem of Mercury around the sun. The way it does beyond that is it explains something that Newton didn't explain. Why does the apple fall from the tree? Einstein gave us Newton gave us a formula, but he did not tell us why the two objects are attracted to each other, but rather just a formula for how they are. Einstein's theory tells us why. It's a warpage of space-time. I show it in this picture here on this grid. It's a little bit like a trampoline. If the Earth is sitting on the grid, it warps the shape of space and time. Each of these points are changed in both space and time. And if I put an object out here, it'll roll toward the Earth. And that's basically the reason the apple falls to the Earth. And it's the reason the moon stays attracted to the Earth while it's trying to go around and goes in an orbit around the Earth. So that basically is an explanation that Einstein's theory gave that Newton's theory didn't. Next, it solved a conceptual problem in Newton's theory. Newton's theory, when the apple falls, you understand that the apple fell immediately. There's no time that passes. But if we start talking astronomically, it starts to become a problem. For example, imagine that the sun were to burn out right now. In Newton's theory, you would know it immediately. That's not the case for Einstein's theory or for nature. It takes 8 minutes for light to travel from the sun to us. So it would take 8 minutes for us to see that it's dark. And likewise, the gravitational signal, whatever happens gravitationally, should also travel at the same speed, not instantaneously. So in Einstein's theory, gravity, or gravitational waves, it'll be traveled at the same speed as the speed of light. So these are the conceptual problems that Einstein solved. And then he made, that's a nice theory, but then it made a new prediction. And that new prediction was that light, not just masses near each other, would bend if they came near a place where the field or the space-time got distorted by a massive object. So imagine that you have light coming from behind the sun, past the sun. The sun is massive, distorts space and time around it, and that bends the light as it comes. That amount of bending he calculated, and he suggested that it can be seen if you look at when the sun is dark, which means a full eclipse of the sun. That experiment was done by Sir Arthur Eddington, and he saw that not only did it bend, but it bent just the amount that Einstein had predicted. And in fact, this bending of light around the sun is what made Einstein worldwide famous. Basically, this is the New York Times article that described the strangeness of light bending, which of course is something that is hard for us to imagine. We think of light going in an absolutely straight line. So beyond that, what happens often in science is what's a new discovery leads to it becoming a new tool. And so in modern astronomy, the fact that the light gets bent as it goes around objects has become a tool called gravitational lensing. If we have a source and it goes by an object that's, say, dark, the light that goes by it gets distorted, it gets bent, the image of the source looks different from that. And by studying the image, one can tell something about this dark body that was sitting here. And that technique has been used a lot in modern astronomy. It's called gravitational lensing. And this is two pictures of lensing around around an object. One up here, and a second one which is famous and can almost be seen with the naked eye, and that's the Einstein cross. Now, let me go on to the new phenomenon, and that's the waves that come with gravity, like light waves and electromagnetic waves come from electromagnetism. It turns out that gravitational waves are a necessary consequence of special relativity with its finite speed of information travel. Gravitational waves come from the acceleration of masses and propagate away from them at the speed of light. Let's again reflect on electromagnetism. Electromagnetism comes from taking two sources and oscillating them, a dipole, and it travels at the speed of light. So the difference here is we have to create what's called a quadrupole moment, and that happens when you have two objects going around each other like this, and then the waves go out like gravitational, called gravitational waves. These distortions that I'm showing here are distortions in space-time itself. They don't have something connected with them, as far as we know, like the photon is to electromagnetism. So it's much more like what happens when you throw a pebble into a clear pond. The pebble goes to the bottom, but the rings of water on the surface go out, much like this picture here, and not carrying anything of the object, but a result of the phenomenon that happened when the pebble went in the water. It's likewise here, when the two objects are going around each other, they distort space and time, traveling out at the speed of light. So gravitational waves are ripples in space-time itself. They stretch and compress space-time. The amplitude of the waves that we'll look at are 10 to the minus 21. I emphasize the number being very small. That's 10^21 zeros point something. So it's a tremendously small number. That's why we live in a world where we don't see big distortions because of gravity, because it happens to be very weak, which is good. But that's a finite number that if we're good enough, we can calculate. It changes the distance between any object by this strain, which comes from gravitational waves or Einstein's equation, where delta L is the strain times L. So if we have an object that, say, a circle of beads, free to move, and a gravitational wave comes through, they would stretch in one direction by a distance delta L, where delta L is this little h, 10 to the minus 21, times L. And that means if it's 1 meter in size, the stretching would be 10 to the minus 21 meters. That's a terribly tiny number. And it explains why when we made a gravitational wave detector, it's kilometers in size instead of meters in size, making this number more like 10 to the minus 18 instead of 10 to the minus 21, which is still a tiny number. It's the size, basically, of a proton. So it's a tremendously small number that we have to measure, and it takes very good measurements to do that. We do it by a principle called interferometry. Now, let me reflect just a minute. If we want to measure something very accurately, it can be very hard. And so we have institutions, big institutions that do it for us. The National Bureau of Standards in the US, and a big agency in Paris is the main one that measures for us and tells us how we determine how much a kilogram is or how long a meter stick is. Those are very difficult to tell. It turns out that it's much easier sometimes to tell the difference between two objects that should be the same or almost the same. And that's the trick that we use. Interferometry measures the difference between light, the time it takes light to go in perpendicular directions, going the same distance. And so if light goes from a laser on the left, it's a mirror. You divide it in two and send it down the two arms. If the two arms are constant, it should come back at exactly the same time. I can invert one compared to the other and they'll just cancel. And then my sensor that sees the amount of light would see nothing, they just cancel. But if they change, like I've shown here, which is what happens with gravitational waves at a frequency that I'm showing of a couple times a second, then the time it takes to go down one arm is different than the time down the other arm. And what we see is they don't quite cancel here. We see a signal, and that's what we look for. The size of this for us is 4 kilometers. I mentioned that it's big kilometers, which means we have to measure a different distance of a few 10 to the minus 18 meters. In order to do that with an instrument like this, we have to be able to do it to essentially 1 part in 10 to the 12 of the wavelength of the light that we're using in the laser. That's many orders of magnitude better than anyone's ever done in the past. And that took us many years to develop the techniques to do that. The second problem is that I can't measure the distance from here to here if everything's moving anyway. And it turns out the Earth moves too much. So in our case, we have to suspend this interferometer, that's the word suspended here, from the Earth, basically float it. And we have to eliminate any vibrations from the Earth, again, to 1 part in 10 to the 12. And these two problems are what made it so difficult experimentally to develop an instrument that was good enough to measure gravitational waves. Finally, when we used interferometry, we started building the device that detected gravitational waves in 1994 and detected gravitational waves 21 years later. The two instruments that we have are identical. One's in the Northwest in Hanford, Washington, and the second one is in Louisiana, Livingston, Louisiana. The distance between these two is 3,000 kilometers. That's a time, if light was going from one to the other, of 10 milliseconds. So if I have light coming this way, or a signal coming this way at the speed of light, it would come to the Hanford Observatory 10 milliseconds before it would come to Livingston. Or if I come the opposite direction, it would come to Livingston 10 milliseconds before Hanford. If it came down the middle, it would be at the same time. So we require that the two see the same signal within 10 milliseconds. And the difference in time tells us something about where it came from. And that's basically the technique that's used. These are the two detectors. They're identical technically. These are the long 4-kilometer arms. This is where all the optics and lasers and so forth are, and a 4-kilometer arm this way. This one's identical in Livingston, Louisiana. The terrain is very different. This is swampy forest, and this is high desert. But the instruments are the same, and they basically work the same and give the same sensitivity and result. This is the sensitivity then of a gravitational wave detector. All the lines here are just all the things that limit us. And the region where we can sense something is the colored region up here. This is this little h that we measure. This is 10 to the minus 21 right here. So this is the place where we can see something. All these things limit us. If we look at the highest frequencies, we're limited by how much light we have, the lowest frequencies by the residual shaking of the Earth, and the intermediate frequencies by the fact that we're working at room temperature. So this is basically the area that we look at. And you can notice on the bottom that goes from tens of hertz to thousands of hertz. And that's just like the ear. And it turns out that that's not an accident. We're doing nothing acoustic. So we're not like the ear, but evolution has taught us that if we want to communicate with each other, then we have to do it where the earth is the quietest, and that's the audio band. And likewise, the earth is quiet to do something very different than audio, and that's to look for gravitational waves. So it turns out when we're looking on Earth, that's the frequency band we're able to explore. And this is the exploration. You can see our curves look a lot like this. The coordinates are a little bit different. And this is a year-by-year improvement as we made the detector come to the design over a period of 2 generations and 21 years. This is just a picture, and it's the only one I'll show you, of a technical part, which is how did we manage to make it isolated from the Earth in 1 part in 10 to the 12th. In this picture, you'll see that these are springs, and those springs are just like shock absorbers in your car that take the shock when you go over a bump, and they transfer to lower frequencies where they don't bother you in the car. We do the same thing. If there's something in the audio band, the shock absorbers take it and move it out of the audio band as well as they can. And then all these other little devices in here are the fact that what we learned we had to do even more than that was to actively sense any gravitational, any movement of the Earth with seismometers and then push back and correct for it. So this is a very sophisticated instrument that basically passively gets rid of as much as it can with shock absorbers and then actively gets rid of the rest, or down to 10 to the 1 part in 10 to the 12th, by sensing any remnant movement of the Earth and pushing back against it so that our mirrors that were reflecting the light stay still. This is where we were about halfway between 1994 and when we discovered gravitational waves. We had reached this little line shown here, and in a different configuration, we could go a little bit lower here, but not as well at low frequencies. And so we had reached the design we had done before we added, for example, the active seismic seismic tools to be able to reduce further the seismic noise. At high frequency, we improved the power of the laser. At middle frequencies, we made bigger and better mirrors. And at the lowest frequencies, we basically provided better seismic isolation by doing the active seismic. And lo and behold, the improvement was a factor of 100 on the scale that I showed you at low frequencies. And that was essentially how far out we could look in the universe. We could look 100 times further when we reduced the amplitude that much. And basically a factor of 100 further out in the universe is a factor of 1,000,000 in number of galaxies, stars, and so forth. And so it's not surprising that once we made this big gain, we were able to then detect gravitational waves, even though we had run for years and not seen them before. So this was then in 2015, September 14th, our first observation of gravitational waves. I'll just show you this quickly. What happens when gravitational waves come through? They're waves, so they go up and down. They basically get bigger as the 2 objects get closer to each other, and then they finally merge. So what we're seeing is the last parts of the merger of what turns out to be 2 black holes, making this up and down narrower and bigger, and then merging and ringing a little bit afterwards. This is the interferometer in the state of Washington. This is the interferometer in Louisiana. And basically if you add the 2 together, they fall on top of each other. If you slide one slightly compared to the other, which is telling you what direction it's in. So that was the discovery of gravitational waves. The line below, this is it again, shown on a different graph. And the line here is, the lines here are the calculations coming from Einstein's theory. And you can see that this looks for this being a little wigglier because it's just experimental. It looks very much like the curve here. And if you subtract one from the other, you get nothing but just random up and down. So this was the first event ever seen of gravitational waves. From that, we could calculate all kinds of things, and I can't take the time to tell you, but we identified it immediately as two black holes, 136 times the mass of our sun, 129 times the mass of our sun. That adds up to 65, but the final mass of the black hole ends up being 62. So 3 solar masses of energy went off in the form of gravitational waves. And then we can even tell something about the spin, 2/3 of the maximum spin it could be, and how far away it is. That's about 1 million light years. And that was the masses of the two objects. So that was the discovery of the first gravitational waves. The second one we saw a few months later, and you'll see it's typical in physics. It's not exactly the same. This has many, many wiggles. And the many wiggles are because they were lighter. The two black holes were lighter, and so they stayed in the detector longer before it came to a time to merge. And that was the second event ever seen. Since that time, we saw a whole bunch of them. They were all black holes. Until we saw this one down here, which I'm going to talk about separately, where these are all tenths of a second. This is some different scale, 10, 20, 30, 40, 50, and it stayed in our apparatus much more than a minute. That meant it was a very light object to stay so long in our detecting bands. This shows something about what we learned just from the very first ones. And remember, I was telling you that looking at the sky in different ways, we are bound to learn something more in astronomy. So here we learned quite a few things just from the very first observation. First, that stellar binary black holes exist. That wasn't really established before. That they come in pairs, one going around the other, just like the moon around the Earth. That they merge, that's going to happen in Einstein's equations, but that they merge actually within the lifetime of the universe because we've observed it, and that they're very heavy. This was a huge surprise to astronomers because very heavy stars, this is 20 times the mass of our sun, are very hard to reconcile with how they can be stable. They tend to be unstable, but yet it turns out they exist and they form these black holes that we saw. So once we make these observations, then we have to determine where things are. So now I want to talk about, okay, we make these observations, how do we connect them to electromagnetic observations? In order to do that, we have to be able to find the answer very quickly because we can't go back and tell them to go look at the sky after everything's all gone. So we basically have 3 detectors that search. One's in Italy and 2 in the US. We then very quickly determine what was the difference in time when the signal arrived in these, and that gives us a position on the sky. Then we spend some time, up to about 30 minutes maximum, but mostly much shorter, deciding what it was and whether it was a real event and whether it's worth telling astronomers that might have to turn their telescopes. And we do all that within minutes. And then we spend hours, days, maybe even weeks determining whether the whole thing makes sense by much more detailed calculations. And about 10% of the time, we were wrong in alerting astronomers. We alerted them, but it turns out it was not a good candidate in the final line, but we're pretty good at announcing them. And of course, if they turn their telescopes, we better be pretty good, or they'll get tired of pointing them. This is the early data when only LIGO existed. That's the 2 US detectors. And what we saw were big bands in the sky, about 1200 square degrees, when we saw some of these gravitational wave events. That wasn't good enough to tell astronomers. It's when a 3rd detector was added in Italy that gave us the ability to determine where something happens in the sky much, much greater. And that happened in 2017, August 14th, 2017. So the detector in Italy came on at that time, and we quickly saw an event where we had gained the position by comparing with the time they saw the event compared to when we saw the event in the US. That was the most accurate that we've ever seen an event, and none of these black hole events ever gave anything that gave a signal that was observed in any sort of electromagnetic observatory of any type. That's, of course, what you expect. That's why it's called black holes. And so you don't expect to see it except in some other kind of detector like gravitational waves. But then, only a few days after we had the Italian detector on, we saw that the gravitational wave signal was the gravitational wave signal from an event that happened simultaneously basically was the one that I showed you that was very different. We located it very well in the sky. And from that, we basically could tell that it was also observed gamma rays from a satellite called Fermi. And they even came from the same region in the sky. This is the region seen by Fermi. This is the region seen by LIGO. And basically from that, we were able to determine that there were gravitational waves simultaneously with high energy photons. That was quickly put together by looking at all the other wavelengths, looking at neutrinos, looking at visible light, looking at radio waves, looking at gamma rays, turning telescopes, roughly half of them in the world, to look at this region of the sky. And with that, signals were observed at different times in different frequency bands, but coming from the same source. All of this, when it was put together, satisfied a theoretical conjecture that what was being observed was called a kilonova. A kilonova is when two neutron stars merge together instead of two black holes merge together. And that picture is what gave us the picture of a kilonova. Then these many measurements were looked at technically to compare with the different wavelengths, the different times, the amplitudes, the different colors, and everything agreed with the kilonova. This is a picture of the frequency distribution as a function of brightness, where it's brightest at the different frequencies. And again, it fits this kilonova emission. An interesting fact in that is that we as physicists have always had trouble describing why it is that in the Earth, we have mines and go find heavy elements. Of course, the one we care about the most is gold or platinum that we use in rings, but all the very heavy elements. They're not explainable by what we understand about the sun, because the sun burns by what's called a fusion process. The fusion process starts by burning hydrogen, then helium, then heavier elements. Eventually, as it burns up its fuel, it gets up to iron. Then fusion doesn't work anymore. At that point, only gravity is strong and the fusion dies and the star collapses. And that's called a supernova, and it makes a big bright light, which is observed. So that basically doesn't easily make heavy elements, although we've made arguments that maybe it does. It turns out that you can ask, how do we know all these elements in the lab? In a chart here, and it's because we know how to make them in the lab. We can take a heavy element, iron or something, and bombard it with neutrons, and we make heavier ones. And basically, that's the trick that's always been used to make heavy elements. Neutrons bombarding a target. Sounds a little bit like neutron stars. So in our case, we have the ability then to make something like platinum, gold, maybe from the kind of collisions that we observed. And in fact, in the kilonova picture, the neutron star mergers are incredible factories to make gold. So for example, the LIGO observed neutron star merger, the one that we saw, actually in calculations produced 100 Earth masses of gold. Of course, they're not in the Earth, they're out there, but neutron stars that collided in the distant past produced the gold that then ended up in the Earth. So this now is our best explanation of neutron, of where gold comes from. Now we continue to improve LIGO. We started a data run almost a year ago, and we recorded 56 events in a little less than maybe 45 weeks. We had to turn off this spring because of the COVID-19 problem, but at that point we had 56 new events. We're off now, and we'll be off for the next year, making further improvements, and an even higher rate. We should be able to see one event a week. So far from this larger data sample, we're looking at exceptional events. So here's two examples. One is that we've seen more events like the neutron stars, which should be in a band of about 2.75 mass total, some distance around that. All our events fit in that except one. It's about 5 sigma away. We don't know yet why or whether it's something else. So that's one event. We have another one where we have a heavy black hole and a small object going around it. And the small object that's going around it, almost 10 times smaller than the black hole, turns out to have a mass of about 2.5 solar masses. That's the area too heavy to be a neutron star, supposedly, and too light to be a black hole, because it wouldn't make a black hole, it wouldn't have strong enough gravity. And so what are we seeing in between? That's basically for the next talk when I come back, but that's what we're showing now, just the exceptional events based on one event that might be telling us something. Now let me talk about the future for just a few minutes and then I'll end. We soon will have 5 different major detectors around the world. We're building a 3rd one in India, and the Japanese are turning one on in the Kamioka mine where they do neutrino physics. And so there'll be 5. With 5 detectors, we'll go from today, where these little stripes are how well we can see where something came from around the globe today, and what it will look like by the mid-2020s. So we'll be able to point very well in the sky to alert astronomers anywhere an event comes from by 2024 or so. We also, by having more events, can look for other phenomena. So far, everything I talked about was an in-spiral event. But I mentioned supernova. We can see supernova with gravity because they'll give gravitational waves. We can study spinning neutron stars, and maybe even signals from the early universe. So we have a rich history as we improve. We'll do that by incrementally improving LIGO and Virgo in Europe. And within the next decade or so, we know already how to make the next detector. This is an example of a design for the next detector done in Europe, which would be underground instead of where it is now. Longer arms, like 10 kilometers, the shape of a triangle instead of an L shape, be cooled, which makes the noise much less, and have special configurations for low frequency and high frequency. Such detectors will enable us to see much further out in the universe, which means much earlier in time. By saying earlier in time, we basically start to be able to do cosmology or early universe physics with gravitational waves. I'll mention that in a minute. That's us on the Earth. There's also an experiment which will be in space in the early 2030s called LISA, and it looks at a different frequency band. So now thinking about electromagnetic frequencies for astronomy, we want to do that also with gravitational waves, look at a different frequency bands in different detectors. LISA will give us 10 to the minus 1 to 10 to the minus 4 hertz. We were 10 hertz to 10,000 hertz. And there's another technique of looking at pulsar timing, which is looking at existing pulsars and distortions in their timing. They can give even lower frequency. All of this points to a very rich future. This is just a picture of what will be done in space in LISA, 3 arms in a triangle, 2.5 million kilometers separated. This is the pulsar timing array as it'll be done. And altogether, we'll be able to cover in the future, eventually, a broad range of frequencies, very much like I pointed out in the very first slide in electromagnetism. This is the different instruments that might be able to do that in the coming decades. And this is the different science as you go to different frequency bands. The most challenging and maybe the most interesting is to get to the very early one. And the reason that's so interesting is that gravitational waves are probably unique in being able to give us the information that we need to really understand what the Big Bang is, what the early physics is that gave the beginning of the universe. We now study it using photons. Photons only send us back to actually 300,000 years after the Big Bang. The universe was opaque before that, so we couldn't see. Neutrinos would go earlier, but they don't appear to be experimentally possible because the neutrinos are so low in energy. Gravitational waves go to the very, very first instance because they're not absorbed at all. So if we can detect gravitational waves from the early universe, we can learn how the universe began, how it evolved in the very, very earliest times. And that may be the most profound question we have in physics. So I'm basically finished. I've shown you the birth of what I think is a new astronomy. That's an astronomy with gravitational waves, 400 years after Galileo, on the shoulders of people like Einstein. And I hope you've enjoyed it, and I'll answer questions in a few minutes. Bye-bye.